Okay, so here's what we got today. We're going to go through the assignment from yesterday, and then use that as kind of the basis to the springboard and how we work with gravity. And the beauty of the gravity calculations are that they're the exact same 4 equations that you've already done, so there's nothing new to learn, it's just how you apply them in a different situation. Okay, so let's start off talking about, because it's one of the more difficult ones, and that's question number 17. Okay? So if you look at what's happening on number 17, so here's this car, and it's moving at 20 kilometers per hour, right? And the first thing I'm going to ask you to do is draw these velocity vectors, okay, to show what's going on. Do not make these complicated. Here's all I'm looking for. Is you come in here, you draw V1, okay? Now, when you draw V2, one of 3 things could happen. Either V2 is going to get bigger, V2 is going to stay the same, implying this at a constant velocity, or V2 is going to be smaller. That's it. Okay, those are the only 3 things you can have. Eventually, you can change the direction, but we're not there yet. So, what's that second velocity vector going to do? Bigger or smaller?
Smaller.
Smaller. Why? Slow it down. Okay. So just come in here and go, okay, there's V2. Now, at that point,
I'm just walking.
okay, all right. At that point, which direction is my acceleration vector going to point? In the same direction as my velocity vectors, or the opposite direction? Opposite, because you're slowing down. Oh, come in here and go, okay, here's some negative acceleration. That's all you have to do. Do not make this complicated, okay? Do not make this complicated. Now, what are you going to have to do with the kilometers per hour? Change that into meters per second, okay? Which, if you do that right, should be 5.56 meters per second. Because if that's wrong, everything else is going to be an absolute train wreck. Multiply by 10, divided by 36. Now, if you look at the VDAT chart, okay, VDAT. So, you've got your initial velocity, which is 5.56. What's your final velocity going to be? 0. Why? Rod to rest, right? Okay. Can't get much slower than that. I don't know, this freshman class might be able to. Now, what else do you know? Distance of 3 meters. Okay. Now, this says 5.6 meters per second. Kyle ran faster than this. Okay. So this isn't like this car is going like really, really fast. Okay. This car isn't going that fast. You're stopping in 3 meters. 3 meters is about from me to that wall. Okay? So that's the distance over which the car is going to stop. So, you're trying to find the acceleration. Now, do you care about time? Is time mentioned in this thing at all? No, don't even worry about time. Okay? It's not part of the story. So right away, when time isn't part of the story, what equation do you want to go to? That equation. Okay, now before you calculate your acceleration, is the acceleration of this car going to be a positive or negative number?
Negative.
Negative. Why? Slowing down with positive velocity. Okay, so you know you're going to go v squared equals v naught squared plus 2ad, right? So, Hannah, what's this equation look like solved for acceleration?
V squared minus v naught squared divided by 2d.
Fantastic. Absolutely perfect. Okay? You plug in the numbers and you find that acceleration. That should be about negative 5.5 meters per second squared. Okay? So that's what you should get something around negative 5.5-ish for that acceleration on 17B. I'm sorry, that's actually closer to 5. It's closer to 5 than it is to 5.5. I was thinking of another problem. So it's about negative 5 meters per second squared. Okay, a little bit above that. Now, the next thing you want to do is figure out how far it's going to take if you double the speed. Now, so here's what you might be tempted to do. You might be tempted to go, wow, if I'm going 20 kilometers per hour and I stop in 3 meters, if I'm going twice as fast, of I'm going 40 kilometers per hour, I should stop at twice the distance, which would be 6 meters. Okay? That's what you're tempted to do. It's like, oh, that seems logical. If I'm going twice as fast, it should take twice the distance to stop. Okay? Seems reasonable, right? Okay? If I work for 1 hour, I make $10. If I work for 2 hours, I should make 20. There you go. But, anytime you see something that's squared, be very, very leery of saying, oh, it's just a straight linear relationship. Okay, so anytime you see something that's squared, be very, 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 very careful. Now, so you want to figure out that distance. So what you need to do is go back to here, and you're going to have v squared minus v naught squared over 2a is going to equal your distance. So this is like the smash mouth physics way to do it. Now you've got that acceleration you're going to put in here. Okay, so you're going to take that acceleration from the previous problem. Your final velocity is still going to be 0. Your initial velocity is going to be about 6 or 6.5, 7 meters per second. Okay, it's actually going twice as fast. And then you need to find that distance. So this is what we call smash mouth physics. Okay, you put in the new velocities and you find that value, and your answer should be around 12. Okay, so your answer to 17C should be around 12. Okay, now that's it. Yes.
Where did you get the 6 meters from?
What do you mean?
For the velocity? Did you say the initial velocity was somewhere around 6?
No, I'm sorry. It's twice that. It should be like around 12.
Okay.
I was thinking the first one was around 6. The other one's going to be around 12.
All right.
Yeah, I'm sorry. That's thank you, Paige. Yeah, your new velocity is going to be around 12. So that's the smash mouth physics approach. And some people like that because they really, really, really like numbers. Now, here's the more like elegant way to look at this, okay? And some people like this. So I'm just showing you an alternative way to get to that answer. So if you look at v squared minus v naught squared over 2a equals distance. So this is my initial set of conditions, okay? I don't know what my velocities are. I don't care what my velocities are. I just know this is going to be my initial set of conditions, and it's going to stop in some distance. Now, the new distance, okay, what we're going to call d prime, and we're going to use this system a lot. So that becomes v squared. But now, if you notice, I'm going to double that velocity. Okay, instead of v naught, I'm going to write that as 2v naught squared divided by 2a. Now, when I square 2v naught squared, what do I get? 4v naught squared, right? Over 2a is going to equal my new distance. So look at this. My initial distance was v squared minus v naught squared over 2a. My new stopping distance is going to be v squared minus 4v naught squared over that same 2a. So if this side goes up by a factor of 4, to balance everything out, what has to happen to your new distance? It has to go up by a factor of 4. So the beauty of this is that once you realize this, because it's squared, I want to double my velocity, that new distance is going to go up by a factor of 4. Okay? So what that means is that I don't have to actually know what the distances are. I just know that my new distance is going to be 4 times greater. So if you look at that initial distance of 3 meters, that new distance is going to be 4 times that. Well, what's 3 times 4? 12. Okay? So that's the other way that you can figure out that distance without actually having to crunch the numbers. Because of the fact that that's squared, if I double it, my distance goes up by a factor of 4. Now, keep that in mind when y'all are driving, okay? So as you go faster and faster and faster, okay, you get out on the highway, every time you double your velocity, the stopping distance in front goes up by a factor of 4, okay? So if you go from 30 miles per hour to 60 miles an hour, it's going to take your car 4 times the distance to stop. So as you go faster and faster and faster, you want to leave more and more gap between the person in front of you Because if something happens, it's going to take you more and more distance to come to a stop because it's v squared. Okay, so there's just life lessons from the field of physics. Okay, on number 18, that time, because 18b hinges on A, so if 18b is right, that time should be between 2 and 3 seconds. And on 20, that time should be between 1 and 2 seconds. Okay? So I've got to give you a ballpark idea of where they're at. Now, let's talk about number 11 with the softball flavor. So, C is moving in at 4 meters per second, right? Going to come to a stop. So again, what are the velocity vectors going to do once she starts to slide? Bigger, smaller, stay the same? Smaller. She's slowing down, right? Okay. You don't slide into second base and speed up, which would be kind of cool, but very, very dangerous. Okay. So she's going to slow down to 0. So you know the initial velocity, you know the final velocity, you know the time. So your acceleration on number 11 should be around 8 meters per second squared. Okay? All right. Maybe positive, maybe negative. You all can figure that out. So what I'm looking for on that velocity time graph, again, you don't have to draw this on another sheet of paper unless you want to. All you have to do is just do something like this. Here's 4 meters per second. There's a half a second. And my slope is negative 8 meters per second squared. Okay, that's all you have to have on that velocity time graph. Okay, that's all you have to have. That's it. Initial velocity, final velocity, slope, time. Okay? Now, you want to figure out how far she's going to slide. If you want to, you could use, how could you use your velocity time graph to figure out how far she's going to slide? Abby Sherms.
So repeat the question, sorry.
Huh?
Repeat the question, sorry.
How can I use this velocity time graph to figure out how far she's going to slide?
You could use it to...
You're making this horribly difficult. Abby Sherms.
Finding the area?
Yeah.
Okay.
What does this look like?
A triangle,
Triangle. How do you find the area of a triangle?
1/2 base times height.
Yeah, so take 0.5 times 4 and take half of that. Okay? There you go. You have your velocity time graph. Use that to find your displacement. If you wanted to, you could use that equation. You could use v squared equals v naught squared plus 2ad. You could use distance equals 1/2 at squared plus v naught time. You could use distance equals 1/2 v plus v naught times time. There's 3 or 4 different ways you can calculate the distance. I just use this because that's simpler. Okay? Oh, it's the area of a triangle, 1/2 base times height. So the other thing is that it isn't dependent upon the acceleration. So if I use the acceleration and it's wrong, then I've screwed up the distance. So the beauty of this is that you work off of known values. Okay, now on D, you want to figure out how fast she's moving at 0.3 seconds into the slide, right? Now look at this. All this is like a slope intercept form. So we're trying to figure out how fast she's going at 0.3 seconds. Now let's just think this through. At 0.3 seconds, what does her velocity have to be between? Has to be between 0 and 4 meters per second, right? That's where it has to be. Because at 0.5 seconds, she stopped. Okay? So my velocity has to be somewhere between 0 and 4. Right? It's the only way it's going to work. Now, here's the deal. What would it mean? Let's say you screwed this up, and you really have to screw this up. But let's say that you come up with a negative velocity at 0.3 seconds. What would that physically mean that she's doing?
Going back to...
Yeah, she's going backwards. So you're going to tell me that she's going to slide at 4 meters per second. At 0.3 seconds, she's going in the opposite direction. But yet, at 0.5 seconds, she stopped at second base. Wow. Okay, doesn't make much sense, right? Or worse yet, you get an answer faster than 4 meters per second. It's like, okay, that's kind of cool. You start to slide, at 0.3 seconds, you're going faster than when you started, but then you're going to stop when you get to second base. Huh, wow, maybe not so much, okay? So that's a situation where you want to step back and look at your answer and go, wow, does that physically just make any sense at all? Okay? All right. Let me see. Make sure on 15 that you've labeled the slope of that graph. That gets missed a lot. Your acceleration on number 9 should be around 6 meters per second squared. And on number 12, that distance on 12B should be less than 1 meter. Okay, hip? I don't care. As long as you have the correct number of significant digits and your answer is right, I'm cool with it. Okay. Anything else at all you want me to go over? Any questions at all? Lingering questions like maybe yes, not sure. Hip?
Number 5. I
Can I see the figure number 12? Just raised.
On which one?
Number 5.
Yeah?
I feel like if the line circle and negative, then be either or A or C.
No. Here's the deal, okay? So basically on number 5, if you were to draw this visual, here's the velocity time graph, right? All I'm saying is that the initial motion is positive, so you're going to start with some positive velocity. Okay, that's all. You just know you have some positive velocity. Then you're going to have a straight line that's negative, so in other words, it's going to come down here like this. All right? So you're going to have some positive velocity with some negative acceleration. Now, you always assume that that velocity time graph is a straight sloping line. Okay? You always draw straight sloping lines on velocity time graphs because we're always assuming that the force is the same, so the acceleration is the same. Okay? Does that help? Okay. Bless you. All right. Anything else? Going once, going twice? So get that handed in. Abby, shut down that camera for a second. Good. So the next section today is going to be on gravity. Then tomorrow we'll finish up some odds and ends stuff. We'll have one kind of last big assignment. Got a lab tomorrow, review on Monday, test on Tuesday. Okay? So when you deal with gravity, there's two broad types of problems you can deal with gravity. Situation number one, this is what we're going to work through first, is that you just hold something up and you just drop it. Okay? We're going to hold it up, boom, just let go. So even though I won't ever explicitly tell you, V naught is going to be 0. Okay? My initial velocity is just going to be 0. So I'm holding it up, I'm just going to drop it, point, here we go. Okay? Now, for what's going to happen on both of these, your gravitational acceleration, okay, is negative 9.80 meters per second squared. Now, amongst the long list of things that annoy me, do not say, oh, gravity is negative 9.8. That is the most scientifically incorrect thing that you could possibly say in the entire world. Okay? Oh, gravity is negative 9.8. Love of God, no. Okay? Stop. It's not. You can say gravity causes an acceleration of negative 9.8 meters per second squared. But this is not gravity. Okay? It is not. So don't say that. It's just going to be important. But here's what's going to be important. Is that whether I drop it or if I throw it, G is always going to be negative 9.8 meters per second squared. You're not thinking, oh, do I make it positive or do I make it negative? Ooh, I don't know. There's nothing to think about. You just let G always be negative 9.8 meters per second squared. So your initial velocity, if you drop it, is 0. If you throw it, it depends upon which direction that you throw it. Okay? So if I throw the ball up, okay, then I'm going to have a positive velocity. Because anything going up in these, on all of these systems, anything going up is positive, anything going down is negative, okay? There's no exceptions. Any positive, velocity, acceleration, displacement, whatever. If it's pointing up, it's positive. If it's pointing down, it's negative. No exceptions whatsoever, okay? So, if I throw it up in the air, I'm going to have a positive initial velocity. If I throw it down, I'm going to have a negative initial velocity. Now, when it lands, okay, when it lands, both of them, because it lands, it's going to be going down, both of them are going to have negative velocities when they hit the ground, okay? So, the beauty of these problems is that there's no new equations to learn. We're going to use the exact same 4 equations that we've already talked about, okay? The exact same 4. There is nothing new. The only thing different is instead of where you see an A, we're going to put G. And G is always going to be negative 9.8 meters per second squared. And you're always going to be on Earth unless I explicitly tell you differently. Okay? Unless I say, hey, we're on the moon, or we're on Mars, or we're in deep space where there is no gravity. Okay? But unless I explicitly tell you something differently, you just always assume that we're on this strange rock. Okay? All right. Got that idea? All right. So here's what we're going to do. We're going to work just a couple of problems, and you can kind of see how this plays out. So visualize this. I'm going to have Gary the golf ball, and I'm going to have Gary the golf ball 2 meters above the ground. Okay, so I'm like this. I'm going to let go of Gary. Okay, just here, boom. So here's what I want to figure out. I'm going to drop Gary. I'm not going to throw Gary down. I'm not going to throw Gary up in the air. I'm just going to drop Gary the golf ball. So I want to figure out how long Gary is in the air, and I want to figure out how fast Gary is going at the point of impact. Now, don't sit there and go, oh, this final velocity is 0 because it's going to hit the ground, okay? No. What I'm asking for is how fast Gary is going when Gary comes in contact with the ground. So don't sit there and go, oh, that's 0. No. Stop, okay? No. Now, I've only given you one bit of information, and that's the fact that this is going to fall a distance of 2 meters. Okay? So if you look at VDAT, which is just fun to say, V naught, DAT. So I'm going to drop Gary, so what's my initial velocity? 0. Okay? Now, for my distance, for now, listen to me, for now, I'm going to let that distance be 2 meters. Okay? So I'm just going to put 2 for now. Okay? We'll get back to that. Just going to put that as 2. Now, what else do you know?
Acceleration.
Acceleration, which is going to be negative 9.80 meters per second squared. I don't know time, and I don't know the final velocity. Hum. Hum, hum, hum. Now, let's chit-chat. Let's actually start with the velocity time graph. So where's the velocity time graph going to start? Huh? 0. It's going to start at 0, right? Because that's the initial velocity. Now, one of 2 things is going to happen. This line's either going to slope up, or the line's going to slope down. Macy, what's it going to do?
Down.
Down. Okay. Straight line, curved line?
Straight.
Straight line. And what's the value of that slope?
Negative 9.8 meters per second squared.
Perfect. Why?
Because that's the force of gravity.
Yeah, that's the acceleration caused by gravity, right? Okay, negative 9.8 meters per second squared. Okay, that's cool. Now, so I'm starting to paint this picture. So let's talk about the time, right? So I know how far Gary is going to fall, so I know a distance. I know the acceleration of Gary. I know his initial velocity is 0. I'm trying to find the time. So which of those 4 equations involve a distance, an acceleration, a time, and an initial velocity of 0?
The third one.
What did you say, Zoe?
The third one.
Okay, what's the third one?
D equals V naught T plus 1/2 AT squared.
Ah, it's nice. It's nice. Like the equation? The equation is nice. Okay. Now, here's the deal. What's the initial velocity? 0.
0.
That goes away. Okay? Don't have to worry about that. Now, I need to solve that equation for time. Okay? I need to solve that equation for time. So, Katie Sher, what can I do? I hate fractions.
Multiply d by 2 and
Yep.
divide by a.
And then?
Square root of all that.
Beautiful. Okay? So, time is going to equal the square root of 2d over 8. This is not a big dog equation. It's more like a pup. Okay? Okay? This is a pup. But this is a great equation to use, and you will use this a lot. But listen to me very carefully. Okay, listen to me very carefully. You can only use this if the initial velocity is 0. Okay? So if I throw the ball up in the air, I can't use this equation. If I throw the ball down, I can't use this equation. But if you're either dropped, or if you throw it up in the air and then have it fall on the way down where it starts at 0, you can use this equation. This is very, very handy. It's a wonderful equation to use. But you can only use it if the initial velocity is 0. Okay? So make a huge caveat. Okay? Ooh, only if V naught is 0. Okay. Cool. So at this point, I'm going to do something wrong. Do not do what I'm about to do. Okay? Do not do this. I'm going to go, okay, I'm going to take 2 times 2 meters divided by negative 9.8 meters per second squared. So for those of you that are math nerds, which is about everybody in this room, why is this a train wreck?
You have a negative under a radical.
You have a negative underneath a radical. So what are you going to get? Imaginary time. It's like, wow, imaginary time. That's kind of cool. Okay? So, we really don't want to have to deal with that. It's awkward, right? So, there's a couple of things that we can do. The shortcut and easiest method would be just to ignore the negative sign. Now it's gone. It's good. It's good. Okay? What negative sign? I didn't see it. Did you see negative? I didn't see negative sign. There we go. Okay? Now, but here's the problem. If you do that, then our velocity time graph that we said at the beginning, when Macy said it has a slope of negative 9.8 meters per second squared, is now out the window. We just can't ignore it. Can't do that. It's easy. It's the easy way out. But it's not right. Because what you need to do is you need to see these problems as like one big idea. And if you begin to just, piecemeal stuff together, you're never really going to understand what's taking place. So here's our solution. Okay, and there's 2 ways that you can do this. All right? One option is that you make the point of release 0. Okay, so I'm going to start up, I'm just going to make this 0 meters. Okay? 0. Now, anything going down, is that positive or negative? Negative. So if I want to do this, then it's going to land at negative 2 meters. Okay? You're going, oh, weird. It's got a negative position. Not a big deal. We'll make it negative. Now, how do you calculate displacement? Position, well, in this situation, I have an initial position and a final position.
Position.
So I'm going to have position final minus,
Position initial.
so I'm going to take -2 minus 0, I'm going to get -2. Ooh, that's nice. Because now, why is that nice? Now I got two negatives underneath the radical, which produces a positive value. These negatives when we cancel each other out. Ooh, that's nice. Okay. Now you're going, oh, Burkham, I don't like that. Okay. Burkham, I want to make the ground the reference point. Okay, make the ground the reference point. Make that 0. But if you do that, then the initial position is going to be going up, which is going to be positive 2 meters, right? So if you make this the reference point, make this 0, and you make that your initial position, then you're going to calculate your displacement. You're going to go, oh, 0 minus 2, guess what? You're still going to get -2 as your displacement. Okay? So no matter how you set this up, you still get a displacement of -2 meters. What I generally would recommend, because it just makes it simpler, I always make the point of release be 0. Okay? I'm just going to go boom, that's 0. Especially if it's just going in one direction. I'm just up here, I drop it, it's going to go in one direction. There we go. I'm just going to make that point be 0. So, but no matter what, I've got two negatives underneath the radical. That works out to be a positive value. We're all good. Now, somebody crunch these numbers. Now, here's what you're going to do wrong. Mark my words. You're going to do all of this. You're going to take 4 and divide it by 9.8 because none of you are going to take, you all are going to punch in 2 times 2. None of you are going to punch in 4. Okay? It's like, oh, I'm just checking it with mental math. Whatever. Okay. So, you take 4 divided by 9.8, and what you're going to forget to do is you're going to take the square. You're going to forget to take the square root of it. Okay? And you sit there and go, oh, Mr. Burkham, we won't do that. Yes, you will. You lie. You lie. It's going to happen. Remember to take the square root. So, what do you get as this time?
0.639 seconds.
Okay? 0.639 seconds. Okay? Now, that's about, if you consider 1 second is like 1 Mississippi, okay? 1 Mississippi, 2 Mississippi, okay? So this is about 1 Mississippi, okay? Not a whole Mississippi, it's 0.639 of a Mississippi. And that works. So if I hold this up and I drop it and I go 1 Mississippi, okay? So that's about, 1 Mississippi is about 0.639 seconds, and that matches our observation, okay? We didn't get a whole Mississippi, we got a 1 Mississippi, which is 0.639. There's a conversion you can do for that. Okay, so we got the time. Oh! Now, at this point we have options, okay? We have options. So let's go back and revisit our velocity time graph. We started at 0. Macy said so wisely that it's going to have a slope of -9.8 meters per second squared. And now we know our time is 1 Missa, which is 0.639 seconds. Okay? Cool. Okay? Got a number. It's good. It's good. Now, I want to figure out how fast it's going at the point of impact. Okay? I want to figure out how fast it's going at the point of impact. Now, here's my question. Here are your options. Option A is that it's going faster than -9.8 meters per second. Okay? Maybe like -10, -12, something like that. Okay? Option B is going exactly at -9.8 meters per second. Option C is going less than -9.8, like -6, -7, something like that. Okay? So at the point of impact, it's either going faster than -9.8, it's going exactly -9.8, or it's going less than -9.8 meters per second. Okay? Those are your options. So how many vote that it's going faster than -9.8? Anybody on the A train? What about B? It's going exactly -9.8 because that's the acceleration. Okay? Less than negative 9.8? So you either are all right, or I have completely done you a disservice and I have not taught you anything so far this year. Okay? The good news is, this is the correct answer. But here's the $1 million question. Why is it less than negative 9.8? You all were right, but why is it less than negative 9.8?
Because it's not.
Kyle. Oh, that's a good answer, right? So here's the deal. Is your acceleration how fast you're going? No. It's the rate at which your velocity changes, right? So if I start at 0 and I go over negative, if I'm here, I go over 1 second, how far down will I go? Negative 9.8, right? Because that's what the slope means. Every second that goes by, this thing is going to drop 9.8. Now, some people like a money analogy, okay? So let's say gravity was a little bit stronger. Let's say this is actually negative 10, okay? It's pretty close. Let's call it negative 10. So here's the money analogy. Your mom and dad drop you off at the store, and every second that you're at the store, you have to spend $10, okay? You have to spend $10 every second you're at the store. Now, but you show up at the store and you have no money, okay? You have no money to start with. But at the end of 1 second, you're still going to spend $10 because we're Americans and we have credit cards, right? So at the end of 1 second, yes, this is true. At the end of 1 second, how far in the hole are you going to be? Negative $10, okay? You spent $10 that you don't have, okay? So at the end of 1 second, you're going to be down here at negative 10. But you're not there for an entire second. You're at 0.639 seconds, so you haven't quite spent $10 yet, right? Okay? So some people like a money analogy. All right, so here's the deal. There's two ways I can calculate that final velocity. And I'm going to show you both ways. And there's pros and cons to both. So one option is that we use V equals V naught plus AT. Okay? It's a linear function, right? Because it's acceleration times time. What's my initial velocity? 0. I have no money, right? I'm going to start at 0. Do you know the acceleration? Oh yeah, negative 9.8 meters per second squared. Do I know the time? 0.639 seconds. So one option is that you go, V naught is going to be 0. So it's just negative 9.8 meters per second squared times the time of 0.639 seconds. So somebody take negative 9.8 times 0.639. Negative 6 something.
0.26.
Negative what?
6.26.
26 meters per second. Okay. Now, this is cool. It matches with what we said, right? We said it was going to be less than negative 9.8, which it is. But what's the disadvantage of working the problem this way? You calculated the time. If the time is wrong, guess what? This answer is going to be wrong. Okay? That's the downfall. If the time is wrong, this is going to be wrong. Okay? So, is there a way I can calculate the final velocity without using time? Is that what you shake your head? Yes. So what can I do?
Use that equation.
Oh, I can use that equation. Okay? Now, here's the downfall of using that equation. The calculator is going to bite. I'm going to do this wrong, first of all. I'm going to do this wrong. Oh, V squared equals V naught squared plus 2AD, right? Initial velocity, boom, 0. Don't have to worry about that. We're cool. Now, so I got 2 times negative 9.8 meters per second squared times 2 meters. So again, why is this not going to end well? What are you going to have? You're gonna have imaginary velocity, okay? By the way, don't invoke that clause. If you ever get pulled over and the officer says, you know how fast you're going? It's like, no, I have this imaginary velocity thing. In my mind, I'm driving like 10 miles under the speed limit, okay? You are just begging for a drug test. I'm gonna tell you that right now, okay? Cops have no sense of humor and they probably don't understand imaginary numbers, okay? Don't invoke imaginary velocities if you ever get pulled over. Just tell me. Okay, but again, how can we fix the situation? Put a negative sign here, or we can just forget and just make that positive, but then that just wrecks the entire problem. So we're going to make a negative number underneath here. Now, this is where your calculator will lie to you. What do you get as an answer? Tell me what your calculator says the answer is.
$6.26.
6.26. Calculator did not do you a solid on this. But, what's the square root of 4?
2.
2 or negative 2. Oh! So what do you have to do? You just choose the negative root. Okay? So, because it's a square root function, I can choose the positive or negative value. No, I'm just going to make that negative. Problem solved. So, here's the pros and cons to each method. The advantage of using V0 plus AT is that it automatically generates that negative velocity. Okay? You don't have to think about it. It already generates the negative value. The disadvantage is that if this time is wrong, that velocity is going to be wrong. Okay? So it's like a roll of the dice. Okay? The advantage of using that equation is that you go off known values. But the disadvantage is that you have to remember to choose the negative root if it's going down. Okay? So there's pros and cons to each. Personally, I have enough faith in myself that I can remember to pick the negative velocity. Oh, I'm going to have that as negative 6.26. Okay? Now, this is where you can go back and look at the big picture. So, if you look at this velocity time graph, and now we're going negative 6.26 meters per second. So, now I know if you look at this triangle, which is 0.639 seconds across, and it's negative 6.26 meters per second down, what should the area of that be? 1/2 base times height, right? So somebody take 0.639 times negative 6.26 and then divide that by 2.
Negative 2.17.
Okay? You basically get about negative 2 meters, right? So this area is negative 2 meters. Why should that area be negative 2 meters? That's how far it fell, right?
I did that.
So that displacement should equal the area, which is negative 2 meters. Okay? That's how you can check if you got it right. Okay? Makes sense. Now, page the rage. Let's talk about the position time graph. I want to start that at 0. So page the rage. I'm going to give you 3 possible curves for the position time graph. Upper lip, middle lip, bottom lip. Okay? So what's going to describe the slope of that position time graph for this ball? It's dropped at 0 and falls down to negative 2. Upper lip, middle lip, lower lip.
You the bottom lip,
Why?
because you're accelerating at a closer rate.
That is true. What you said is true. But Paige, let's back up just a little bit. Okay? What does the slope of the position time graph give you?
Your velocity.
Velocity. As it falls, what happens to the velocity?
Velocity is increasing.
Is increasing. So the slope should get steeper, right? So which graph shows a slope getting bigger and bigger and bigger? Upper lip, bottom lip.
Would be the upper.
What'd you say?
The upper lip.
Upper lip? This one, right? Because you're starting off slow, right? And then it's going to go faster and faster and faster and faster and faster, right? So this should be your this. So what we're saying, whoa, back up the bus. At 0.639 seconds, and this is where this should all come to one big idea. You're down here at -2 meters. Now, I'm going to come in here, and I'm going to draw a tangent line that's going to hit at 0.639 seconds and -2 meters. So this is where hopefully this all kind of makes sense. What's going to be the slope of that tangent line at 0.639 seconds?
Negative 6.26 meters.
What'd you say, Mason?
Negative 6.26 meters per second.
Fantastic. Why?
Because that's the velocity at that given point.
Perfect. Absolutely perfect. So that's going to be the slope of that tangent line is going to be -6.26 meters per second. Now, if I went out here to 1 second and drew the tangent line, what would the slope of the tangent line be at 1 second? Negative 9.8 meters per second, because that's how fast it's going at that point. Okay? So you see how it all fits together. Here's the position time graph. If I were to find this area on that position time graph, what would that give me?
Meter seconds.
Which is
Nothing.
absolutely nothing. Don't ever find the position on a position time, the area on a position time graph. You want to figure out how far it goes? Oh, it went -2 meters. That's tough. Okay. All right. So shut that down. All right. So here's the deal. So I'm going to take a golf ball. I'm going to throw it straight up in the air with a velocity of 22 meters per second. Okay? That's the only number that you know is 22 meters per second. But from that, I want to find the time up, the time down, the time total, the maximum height, how fast it's going at 1 second, how high it is at 1 second, otherwise known as the Colorado question. How high are you at 1 second? I don't know, dude. Then I want to figure out, it's a good thing I don't teach in Colorado where I would make that joke all the time. And then I want to figure out how fast and how high it is at 3 seconds. I want to draw a position time graph. I want to draw a velocity time graph. Okay? All of that, and I know one number, 22 meters per second. But, let's look at the big idea. When that thing's on its way up, what's it going to do? As soon as it leaves my hand, what's it going to start to do?
Slow
Slow
down.
It's
down.
going to start to slow down. At what rate?
9.8
-9.8 meters per second, right? So we know the acceleration. It's not given, but we know that acceleration, right? Now, here's the other crux of this. Allison, when that, when that ball gets to its highest point, what's the velocity of the ball going to be?
It's gonna stop.
So the velocity is going to, so we're going to go from 22 meters per second to 0. Okay, so at its highest point, the final velocity is going to be 0. Now, when it starts back, oh, a hairball. When it starts back down, this is going to be important. When it starts back down, what's the initial velocity going to be? All the way down, the initial velocity is going to be 0. And it's going to land at -22 meters per second. So we're going to go from positive 22 to 0, and then from 0 to -22. Okay, so we're going to break this thing into like 2 distinct flights. Now, the other key assumption that we're going to make is that this ball is going to come back down to the same height from which it was shot. Okay? Now, if we do this and it falls like all the way down to the ground, the times aren't going to be symmetrical. But as long as it returns, and this is a huge if it returns back to the same height, we assume that everything is symmetrical. Time up, going to equal the time down. Okay? All right. Now, before we do any math at all, let's actually start with the velocity time graph. Okay? Now, we're not going to include the throw. Okay? We're going to look at this thing from the split second that it leaves my hand. So, Kira, this thing is going to start up here at 22 meters per second. This graph can do one of three things, Kira. It can slope up, it can be a horizontal line, or it can slope down. What's it going to do? Fantastic. Why? Because as soon as it leaves my hand, what does it start to do? Slow down. It's going to be a straight sloping line?
Yeah.
Yes. It's going to be a straight sloping line. And Kira, what's the value of that slope? Fantastic. Negative 9.8 meters per second squared. Kyle, where's the ball at that point? Right here.
Maximum height,
Why?
because it's not.
Yeah, velocity is 0. So at this point, I'm at my maximum height. Okay? All right? It's cool. So we're looking good at this point. Looking good, feeling good. We've got an idea of what's going on. Now, let's talk about my time up. Okay? Is my time up going to be more than 1 second, exactly 1 second, or less than 1 second?
More.
More. Why?
It's more than 9.8.
Because if I started with an initial velocity of exactly 9.8 meters per second, if I started at exactly 9.8 meters per second, how long would it take to get to 0? 1 second. You go to the mall and you have $10. Mom and Dad are making you spend $10 per second. At the end of 1 second, how much money do you have? Nothing. So Mom and Dad have sent you with 22 bucks, right? You have to spend $10 per second. It's probably going to take you a little over a couple of seconds to run out of money, right? Because you can go from 22 to 12 to 10 to 0. So I got to figure my time up is going to be more than a second because my initial velocity is more than 9.8 meters per second. Makes sense. Okay. So let's tackle that time up. So if you look at VDAT, so this is going up, okay? So if you look at VDAT going up, so my initial velocity is 22 meters per second. At its maximum height, the final velocity is 0. Question mark, I don't know how high it goes. Do I know my acceleration? Yep, negative 9.8 meters per second squared. And I'm trying to find my time. So what's going to relate initial velocity, final velocity, acceleration, and time? What'd you say? Plus 18, right? You know your acceleration, you know everything except for time. So Hannah, what does that equation look like solved for time?
V minus V naught divided by acceleration.
That is perfect. Equals time. So we have 0 minus. Now, what should the sign of time be? Positive or negative? If you ever get negative time, you have done something horribly wrong. Okay? Time is never negative because that would be really weird. Okay? And if you do get a negative time, just don't ignore the negative sign. Oh, I'll just act like it's not there. No. Okay? No, you have done something wrong. So you're going to have 0 minus 22.0 meters per second divided by negative 9.8 meters per second squared. So this is where this fits together. I'm taking 0 minus 22, and I'm dividing it by negative 9.8. I'm going to get a positive time. So, Macy, take 22 and divide it by 9.8.
2.24.
2.24 seconds. Okay. That matches with what we said, right? We said our time up should be more than a second because my velocity is more than 9.8 meters per second. Okay? It's actually more than 19.6, which is twice that. Okay, so we're cool, right? So we got 2.24 seconds as our time up. Now, if it's symmetrical, if we spin, that did not go well. Where did it end up? Thanks, Mason. So, if it's symmetrical, if we, I'm ready to throw it. I spent 2.24 seconds going up and it returns back to the same height. It should take 2.24 seconds going down, right? So our total time should be 4.48 seconds, okay? It's cool. Now, let's talk maximum height. There's a couple of different ways you can find the maximum height. One option is that you could go to your velocity time graph. You got a base of 2.24 seconds. You've got a height of 22 meters per second. Looks like a triangle. Area equals 1/2 base times height, right? But, what's the downfall of that? What are you basing it on? Time. If time is wrong, that height is going to be wrong. Okay? So how can I find the height without using time? I can use that equation. Ooh, right? So this is what I would recommend to find your maximum height. You have v squared equals v naught squared plus 2AD. Now, here's the deal. You can use this because you know at the maximum height, you know what the final velocity is, you know what the initial velocity is, and you know your acceleration, okay? Now, if you don't know the velocity, the final velocity, you can't use this equation, okay? But since we know that the final velocity is exactly 0, I can use this equation. So what does that equation look like solved for distance? Abby Shirts.
It looks like distance equals v squared minus v naught squared over 2a.
Perfect. You guys are like butter. You guys are on a roll with the algebra. So, we got v squared minus v naught squared over 2a. Should my maximum height be a positive or negative number? Hit, positive or negative? Yeah, look at your velocity time graph. That area is going to be a positive number, okay? Because that's going to be your displacement on the way up. Positive number. Now, this is where the magic happens. Final velocity is 0. Minus that initial velocity of 22 meters per second, squared divided by 2 times, right? Now, look what happens. I got 0 squared minus 22 squared, so that's going to give me a negative number up on top, right? And then I'm going to divide by a negative number on the bottom. Guess what? That's going to give me a positive displacement. That's why it's so critical that you just don't put, 22 squared divided by negative 9.8. That's going to get you a negative displacement. This is why you have to look at this in terms of how this whole thing fits together, okay? Not just a random calculation. So, what do you get?
24.7 meters.
24 point what?
7.
Meters. Now, to give you some perspective, this ceiling is about 2.5 meters tall. So that'd be about 10 times the height of this ceiling. Okay? So that'd be a pretty decent height. Okay? Now, here's how you can verify that this is right. Okay, here's how you can check. Let's find the area if we assume this is right. So half of 22 is 11. So right quick, somebody take 11 times 2.24.
24.64.
Yeah, 24.6, right? Which is basically that exact same answer. Okay? So you can't have one set of equations giving you an answer of like 18 and another set of equations producing an answer of 24. So that's the beauty of what you can do on a lot of these. You can work backwards and say, hey, can I solve this a different way and still get the same answer? Okay, so we have one thing left to do. We need to figure the velocity and height at 1 second. Okay? Now, so think this through. You're starting here at 22 meters per second. I'm going to go over 1 second. How far down am I going to go? 8 to 9.8, right? That's what the slope means. So if I want to figure out how fast I'm going at the end of 1 second, what's the only thing I need to do? Subtract 9.8. Oh, that's kind of cool, right? Because that's how fast I'm going to be going at the end of 1 second, because that's what that acceleration means. If you like the money analogy, you show up with $22. At the end of 1 second, you spent $9.80. You're trying to figure out how much money you have left. Okay? Now, if you don't like that, you go, oh, Mr. Burkamp, I love equations. Well, good for you. So, you can go V equals V naught plus AT. Okay, this is the more legitimate way to do it. So you got 22 meters per second plus negative 9.8 meters per second squared times 1 second. And oddly enough, what's going to happen? You're going to take 22 and you're going to subtract negative 9.8. That's all you have to do, right? That's it. So somebody take 22 and subtract 9.8. 13.2? 12.2 meters per second. Makes sense? Right. Hey, it's less than 22, right? Okay. Now, to find the height at 1 second, there is only one way and one way only. And one way only. There's no variation on this thing. Okay? The only way you can find that height at 1 second is to do distance equals 1/2 AT squared plus V naught time. So this is like a function equation. Okay? This is a function equation. So what you want to look at here is that, number one, you have to use negative 9.8 meters per second squared here. Otherwise, you're going to get numbers that are too big. That initial velocity is 22 meters per second. So what this does is that it allows you to keep track of height at any point in time. Okay? 1 second, 2 seconds, 3 seconds, whatever time it is, you can put this in here and generate the value of your height at this point. So when you have a situation like this, when you want to find heights at a certain point, this is the only thing that you can do. There is no other option. Okay? So in this situation, I'm going to take 1/2 times negative 9.8 meters per second squared times 1 second squared plus 22 meters per second times 1 second. Now, what does my answer have to be less than? What's your maximum height? 20, what was it, 24.7? My answer has to be less than 24.7. So if you get an answer bigger than your maximum height, you have done something horribly wrong. Okay? So basically, it's going to be negative 4.9 plus 22. So what do you get?
17.1.
What'd you get?
17.1.
17.1 meters. Okay? Now, that's how fast we're going. 12.2. Does it make sense that my velocity is still positive at 1 second?
Yeah.
Why?
Because that's not 24.
Yeah, it is. It hasn't reached its maximum height.
So it's possibilities.
Yeah, so I still have a positive velocity because it's on its way up. I haven't reached my maximum height. I'm pretty close to it, 17.1, right? Now, if you want to find the maximum height, you could plug in the time it takes to reach that maximum height. You could plug two, here's the other way that you can find your maximum height. Plug in the time that it takes to reach your maximum height, and you can find the maximum height that way. Now, let's talk 3 seconds. At 3 seconds is the ball, if you go back to your velocity time graph. At 3 seconds, you're over here. So what sign should your velocity be? Negative, because it's on its way down, right? It's on its way down. So the only thing different that we're going to do is to find that velocity. Instead of 1 second, what are you going to put in? 3. I'm going to put in 3 seconds. That's the only thing that's going to change. So somebody take negative 9.8 times 3 and then add that to 22.
Negative 7.4.
Negative 7 what?
0.4.
Meters per second. Does it make sense that that's a negative value? Yeah, because it's on its way back down. Now, if you want to find the height at 3 seconds, how high it is, all you're going to do is put in 3 seconds in here. So you're going to take 3 squared times negative 9.8 times a half, and then add that to 22, whatever, or 22 times 3. And that's going to get you that height. Now, here's an interesting question. The total flight time was 4.48. If you plug 4.48 into that equation, what should you get for your height? 0. Because that's when you're going to be back on the ground. Okay? Got it? Good? Okay. So, Abby, stop that for a second.